Okay, good morning. Thank you so much for attending this session and welcome. And I know there are quite a lot of distraction outside, and but still I need your attention because we will discuss attention in my presentation. And here's the topic. And today I will introduce my research related to assessing construction workers' vigilance level through wearable electroencephalography devices or systems. For the electroencephalography systems, we call them short for EEG systems. Before we proceed talking about the detail about my research, I will give you a short introduction on our current safety management. For our current safety management practice, our intention, no matter for the project manager or researchers, we are trying to create a barrier. This barrier can protect our construction worker from all type of hazards. Such strategy including safety instructions, environment, equipment, and some programs, and also sensors so that we can automatically detect hazard and provide construction worker some early warnings or signals. But if you look at this map, you will realize what we neglect through the whole process is construction workers themselves. Let's assume a scenario. Say we have a hazard penetrate the barrier we created, no matter what approach we created for our construction workers. And that will end up with accident. But in fact, that's not the whole story. Sometimes we will have something called near-miss accident. So why near-miss accident? Near-miss accident is one type of accident that's actually it's very close to happen, but not happen. So why there are some accidents, near-miss accidents, some of them are accidents? Because as a human being, we have the instinctions and we have ability to avoid all type of hazard by ourselves. We have such ability. And according to endless research, they give a detailed instruction on what's going on after those hazards penetrate those barriers. According to his research, we have 3 steps. The first step, the construction worker detects the hazardous signals, and then they will perceive and trying to comprehend those signals, and then they will take action. If they successfully take actions to avoid those hazards, and then that's near-miss accident. If unfortunately, that's accidents. But what's the main difference of near-miss accident and accident? All around those 3 steps, endless research indicates the majority of accidents actually they stop over here. In fact, the majority of construction workers, when they have accidents, they do not realize there are some hazards surrounding them, or they are failed to detect the hazard signals. The reason, there are something called working memory for human beings, especially for our mental conditions. So what is working memory? If we make a comparison between a computer and a human being, we have long-term memory and working memory, or short-term memory. The long-term memory looks like a hard drive of a computer, and working memory looks like a memory of a computer. So basically, we are running all type of programs in our memory. If we are out of memory or our memory overloaded, then our computer will broken down, or they will, if you are using PC, and you will have a blue screen. But for human beings, if we are overloaded, then you do not have sufficient working memory to concentrate on other things. Let's give you one example. This is a chart comparing the working capacity of a construction worker and the task demands. So if we assume the scenario, we give a construction worker a lot of work, and they are focused on too much on their work, and then they do not have sufficient working memory or additional memory to detect hazardous signals. If they are failing in detecting those signals, they have a possibility they will end up with accidents. And this chart gives us a very good guide, because for the capacity and the demand of tasks, the ideal situation is both of them match each other. If there are any mismatch, they will end up with problems. If we have more capacity than our demands, and then you'll find the construction workers are idling. They cannot focus on their work. They are doing something else. So that's indicating a low productivity. If we are overloading them, we have more demand than their capacity. That means they probably will end up with working memory. They have a higher chance to get injured. That's very simple math. But the problem is, if we are trying to measure those working loads of our tasks, we have 2 types of loads. One is mental load, the other one is physical load. Physical load is either to be measured because we have devices such as heart rate sensor, and we can do the calculation. So for the construction workers, how long they already worked, or the capacity of the work, so that we can have an indication on the physical requirement of that tasks. But the problem is mental load. There are no such thing that we can use to detect the mental load of the construction workers. But if we can figure out this thing, we have a lot of opportunity to improve our current construction management. For example, we can improve our safety management practice. We can evaluate our productivity. We can optimize our task allocation, or for the driving behavior, no matter for the construction equipment drivers or just regular drivers, they can indicate if you are concentrating on the job you are currently doing, or we can prepare better training programs for the construction workers. So to measure the mental workload of a task or our construction worker is critically important. We have two approaches to do so. The first approach is using some questionnaire. One of the most famous questionnaire called NASA Task Load Assessment, basically derived by US NASA. They are trying to investigate the working load of astronauts and their different type of tasks. This is a subjective measurement. People need to fill in those survey and get results. And we do have some objective approaches. For example, like we have this type of equipment. Sometimes we can see this in the hospital. It's called fMRI, which is a very large and expensive devices, even if we can use that to monitor our brain activity, but not feasible or practical for the on-site construction use. The other approach is called the EEG, as I just mentioned before. Basically, once there is activity in our brain, there will be a microvoltage shows up on the top of our skull. And those devices can measure those microvoltage, so that based on the voltage, we can indicate what type of brain activities we are currently doing. Previously, we cannot do this type of research because all the EEG system is quite similar as MRI, because they are fixed and they are static. We cannot carry them around. But nowadays, we have some wearable systems. We can use wearable. In the very beginning of my research, I developed one device, and we have the EEG system installed on the hard hat of construction workers, and we use that to collect EEG brain signals. And in fact, the EEG brain signal is not just random signal or just like signal we observe like our voice or image. It's a combination of different signals at different frequency level. And each frequency level, they do have indication on the brain activities of human being. For example, we have alpha band waves, beta band waves, and gamma as well. Each of them are either related to the wakefulness, problem solving, or concentration. So we can use those waves to indicate the concentration level of construction worker. Because we assume if our construction worker concentrate too much on their work in hand, then they will have fewer working memory to take care of the hazardous signals. We conduct a research before. Basically, this is spectrum analysis. We are trying to do the decomposition of the EEG signals. We are trying to find the signals back, especially for the gamma bands. This is the indication on the concentration level of the construction worker. And this is directly related to the attention. What we mentioned is called a selective attention. Basically, if we have a lot of information in front of us, we do have some priorities. We will select the one that's most critical to us. For the construction workers, they will focus on the work in their hand. In fact, this indicator is indirect reflection on vulnerability if they are focused too much on their work. And there is another type of research or another type of attention we call them a sustained attention. Vigilance is one type of sustained attention. In this condition, we assume the construction worker are already aware there are some danger surrounding them, and they need to maintain their vigilance. And for different level of danger, they will show different level of vigilance. So my research in this stage is trying to find out a way we can quantitatively reflect the vigilance level of construction workers. So we conduct an on-site experiment. We recruit 10 construction workers on-site, and we create some experiments like this. There is one simple task we required construction worker to carry 2 iron tubes from location A to location B. On the path of location A to location B, we intentionally create several obstacles. Like the first obstacle is a pile of wood, and second one is an overhead rebar. The other one are other type of piles. And after the experiment, we asked the construction worker to rate how difficulty they view those obstacles. This is an indication on how much vigilance they, in fact, they raise up for conducting this tasks. So we recruit 10 people, and here is some demographic information of these construction workers. And as you can see, they have different trades, they have different level of experience, they also have a different level working at height. Because working at height is a good indication on their sensitivity to the danger. And each of them repeats the experiment for 3 times, for 3 trials. So in fact, for all 10 people, and each of them has 3 trials, we have 30 trials of data for further analysis. Here is the equipment that we are using. Originally, in the previous research for the selective attention research, we have 4-channel EEG hard hat. Now we are switching to another commercial version of EEG monitoring device, and they have 14 channels. And for this 14-channel device, we separate this channel upline location into 4 clusters: left cluster, right cluster, mid cluster, and back clusters. So we are trying to find out which cluster is most directly related to our vigilance levels of construction worker. This is very important because in the next stage we have a newer version of equipment. We have a 4-channel or 8-channel flexible channel upline locations. We need to find out which one is most suitable location to use those devices. Because if we have fewer channel, means we have the equipment is, the price of equipment will be lower. And then, as you can see here, is the raw data we collected, and we divide the whole data into small pieces. Each piece indicates some actions. The first action is idling action, which requires them to stand there, relax for several seconds, and then they will pick up the iron tube. Then they will pass through all the obstacles. Here is a demonstration on the EEG signals we captured from the equipment. And as you can see, since we have so many channels, we can conduct this type of spatial analysis. We are trying to find out, during those obstacle passing activities, which part of their brain, in fact, was activated. And we are using that as an indicator to optimize our design for the vigilance level indication. And we also adopt one mature investigation framework for vigilance as well. And as you can see, this is developed by Dr. Rose. And they developed, they follow, you see, this chart follows the development of the vigilance levels. On the very bottom, like stage B and stage C, basically they are when people fall asleep or when they feel drowsiness. This is the stage we are not worried about. So what we are concentrating on is three stage A's. Those 3 stage A's indicating different concentration level of sustained vigilance levels. And they do have some quantitative threshold using the energy or power distribution across different channels. We can use this to find out the stages. In addition to that, we also conduct spectrum analysis for each separate tasks. And as you can see, the spatial analysis, the spectrum analysis gives us a very good indication on which frequency bands have the most effective reflection on the vigilance. And those frequency power also can be used to do the calculation of vigilance stage. And we repeat this analysis for all 10 subjects and for all 3 trials. And as you can see, this is only one of this subject number 4, and we randomly select subject number 4, and this is one trial. And we are trying to observe their power distribution. A little bit different from what we expected. For the sustained attention, the majority of power distribution is quite even over here. If you look at the experiment we saw before, over here, you will observe very quickly decay of their energy distribution at the high frequency power bands. And if we go back to the sustained attention experiment, you find that the power decay is not as fast. And you may not see very clearly on this this vertical axis, but as I can tell you, they have the slower decay for those distributions for the high frequency bands. Normally, high frequency bands indicating the high or complicated brain activities. In addition to that, we also conduct spatial analysis. For the spatial analysis, we also combine with independent component analysis. Basically, what we are trying to do is trying to find out the major components of the components that makes a major contribution to the vigilance development. And as you can see, we also follow similar criteria. We divide the activities, we divide the signal into the different activities. And as you can see, this A3, A4, and A5, all three activities are obstacle passing activities. And this is just one chart. If you look through all those charts, you will see the majority of relationship for the spatial distribution of energy was distributed on this part, left frontal of our signals. So we collect all the feedback information and the spectral distribution information for all 30 trials. Since we have sufficient data, we conduct a statistical analysis for the logistic regression. Basically, this is testing the odds ratio of different vigilance stages over the other one. The probability that we can observe from different activities or demographic or different channel clusters. And after the testing, we compare three models. Basically, they have different number of variables we tested in this model. And we find for the majority of those three models, the left cluster shows a very significant relationship with vigilance development. In fact, it also can be observed from this chart as well. So based on those observations and the data we summarized, we draw some conclusions. And we also, at the same time, we realize some problems for our current research. The first conclusion is, as you can see, based on the power spectrum distribution and the spatial analysis, we can find EEG signals, they do have a direct indication on this vigilance stage development. And second, we also have the left frontal cluster have most close relationship with the vigilance development. And finally, we also observe some individual differences. I didn't show up in my slide, but what I can tell you is for the intensity of their EEG signals, especially for the raw signals, they have different intensity range. So even if we are using relatively intensity, but still they have a different absolute intensity. We do have some limitations. The first limitation is since this is variable, normally the brain activities is working together with physical activities. And second, the subject we select, they could be biased. That's maybe the result why we have this difference in the signals. So in future, and this is our ongoing research, we are trying to do something else. We assume the signal we collect is another different type of signal, different from the regular EEG signal from static arrangement. We assume it's a combination of physical activity and mental activities. We're trying to use another approach, which we call Vigilance package decomposition. We're trying to create our own alpha, beta, and gamma waves. Use that as an indicator for the vigilance or other attention indications. At the same time, we are using another approach. Since each individual has different intensity, and then we are using this approach called event-related potential. Basically, we are trying to capture the special events or pattern of signals. We are collecting all of them and using some statistical analysis, like ANOVA or the pattern matching, to find out if some certain pattern are matching certain vigilance performance of construction workers. And the final research I haven't put this over here is we are also using motion capturing systems. We are capturing the physical activities and mental activities of construction workers together so that we can conduct some data fusion and reference for each data we collect. Okay, that's all my presentation. Thank you for your attention.
Great timing.